All right, so let's see if we can take a look at these questions. I'll answer number two because number three is just very similar. So, a company produces steel rods. The lengths of the steel rods are normally distributed with a mean of 130.7 centimeters and a standard deviation of 2.2 centimeters. For shipment, 16 steel rods are bundled together. Round all answers to 4 decimal places if necessary. Okay, so first it asks for what the distribution of x is. All right, now when it asks for that, we want to list the mean first and the standard deviation second. So it told us the mean was a 130.7. That's what would go first here. And the standard deviation is 2.2, and that would go second. B, however, is a little bit different because it's asking for the distribution of x bar, of the sample mean. And for that, our mean remains the same. It remains 130.7. We put that there. But our standard deviation is going to be this 2.2 over the square root of the sample size. So 2.2 over the square root of 16. And of course, that's really 2.2 over 4. So if I put 2.2 over 4 in my calculator, let me pull that up. 2.2 divided by 4, or divided by the square root of 16, that standard deviation for the second one would be 0.55. Now, keeping those means and standard deviations in mind, we're going to answer C and D. To answer C, since we are looking at a single steel rod, not a sample, we're looking at just one rod, then we are going to use the normal z-score, and we're going to put 130.9 into it and 131.2 into it. All right, so I'm going to go over to another sheet of paper with our mean and our standard deviation. We'll do that calculation. Okay, so I wrote the information from our question down. We have a mean of 130.7 and a standard deviation of 2.2, and we want to find the probability that a single one of these steel rods is between 130.9 and 131.2. So we're going to use our formula for the z-score, and we're going to plug in our x. We're going to have to do it twice because we're going to have to do a calculation for 130.9 and for 131.2. So let's start with the 130.9. We want to take 130.9, and I apologize for my really bad writing. Trying to write with the mouse on the screen. Minus the mean, which was 130.7. And I do not know why. There we go. Seem to have lost the draw. There we go. 130.7. And that goes over our standard deviation of 2.2. Now notice that I'm using the first standard deviation that we got, the initial standard deviation that we were given. All right, so this is going to give me 0.2 on the top divided by 2.2. And we'll go ahead and stick that into the calculator and get what that decimal is. That is 0.0909. It's a repeating decimal, but I'll just write it out about this far. Okay, now I'm going to go ahead and do the same calculation, but for the 131.2. So let me scroll down a little bit. The only thing that's going to change is that we're going to put 131.2 right here where I had the 130.9. All right, so we'll do that z-score calculation. This time Z will be 131.2 minus 130.7 over the 2.2. And on top, let's see, I believe that's going to give me 0.5 divided by 2.2. All right, so let's see what that is. 0.5 divided by 2.2 is 0.2273. Now, we've got to look up both of these values on the z table in order to find their probability. And realize these are the z values on the z table. They're not the probabilities, even though they ended up being decimals. And because it's between a between type problem, once we find the probabilities for these two, then we will subtract our two probabilities, large probability minus small probability. So I need to look both of these up. I can either use the table, or it's probably just easier to use Excel. So I'm going to go ahead and pull up Excel, and I may not have it open. Let's see. Yeah, I'm not even on there. Let's go over here. Okay. And I'll go ahead and pull up an Excel document. Let's just open one up. And I think our first z-score was 0.0909, so I'm going to do equal norm.dst, and actually I don't think that's, actually the one I want is norm.s.dist, and I'm going to put in that value of 0.0909 and comma, must have hit something bizarre there, true. And then hit enter, and there's that probability, 0.5362. Now let's do the same thing for the second one. The second z-score I got was 0.2273, so let's go ahead and stick that one in, 0.2273. Okay, so equal norm.s.dist, 0.2273, true. And that probability is 0.589905. So I'm going to just subtract those two. 0.589905 is the bigger one, minus 0.53614. And that is our answer to that probability problem. The probability of being between those two values is 0.053691. All right, now I want you to notice that the second, let me find the email. The second one of these questions was for a bundle of 16 of these rods, and we have to find the same probability for the average length to be between 130.9 and 131.2. But the difference is that in C, the calculation that we just did, it was a single still rod. In this one, it is a sample of 16 rods. And for that, we're going to use our standard deviation that we got for B, all right, 0.55 that we got for B. So our calculation is going to be exactly the same process for D. But what is different, let me go back to our sheet for a second, is instead of having in the bottom here this 2.2, my second standard deviation for the entire for the sampling distribution of the mean was 0.55. So I've got to use that 0.55 instead of 2.5. Otherwise, what we do is exactly the same. So this bottom will change to 0.55, and I'll have 0.2 divided by 0.55, and I will get the z-score for that. And then this bottom will change to 0.55, and I'll have 0.5 divided by 0.55, and I'll get that z-score. And again, I will look them both up using Excel, subtract those probabilities to get their answer. So notice, if we have a single value, we use the original standard deviation that we had to begin with. If we have a sample space, such as our 16 rods in this case, we have to use a new standard deviation, which is created by taking the original standard deviation and dividing it by the square root of the size of that sample. So in this case, it was the square root of 16 that led us to 0.55. Okay, now let's go back to the last question on that page. And just, all right, so for part D, is the assumption of normal necessary? Now, we have to have a normal distribution if our sample size is less than 30. That's what our central limit theorem says. So if the sample size is less than 30, then normal is necessary. We have to know that it's a normal distribution. If the sample size is greater than 30, it doesn't matter. We don't have to have the assumption of normality. So let's notice this sample size is only 16. So for Part D, we do have to have the assumption of normal. So the answer here is yes, it is definitely necessary in this instance. All right, now hopefully that helps you through both of these problems because they're both very similar. Um, and then let's go to the other ones that you had. So let's see, number 2 here. Assume that the readings at freezing on a batch of thermometers are normally distributed with a mean of 0 and a standard deviation of 1. A single thermometer is randomly selected and tested. Let Z represent the reading of this thermometer at freezing. What readings separates the highest 47.05% from the rest? Okay, so really we want to know for what value the probability is greater than 0.4705. Now, we can use our Excel to help us with this, but Excel only will generate answers for a less than problem. So if this said Z is less than C, we could just plug this right here into a command that I'm going to show you in a minute, and we would get back the original value of this temperature that corresponds to 47.05%. However, since this one is greater than, the first thing we've got to do is for any greater than problem, subtract this from 1. Because all probabilities will add up for 1, add up to 1. And since we know that our little operation we're going to do is going to give us the probability that Z is less than C, then really we need to just subtract this from 1 to see what is remaining on the other side of it. So 1 minus 0.4705, I will do that. I'll go to Excel if I can find it again. One minus 0.4705. And then we are now going to do a little bit different command because we're going backwards from the process that we did up here. Up here, we found the z-score and we were trying to find the probability. This time we have the probability, we want to go back to the original score. So we do equal norm, and we're looking for this one right here, norm.s.imb. Takes us, it's the inverse operation of what we did before. So we'll plug in 0.5295. And so the original value is 0.074013. And oops, this is not the same one we had pulled up a second ago. I'm not sure exactly where it went. Now this last one, you're going to do exactly the same one as the same way that we did the one we had a few minutes ago. Notice that the mean is 0, standard deviation is 1, and again, we want to know what is the original z that is greater than the number we're looking for, such that the probability is this. Now, since it's greater than, again, before we get started, we have to subtract this from 1, and then whatever that decimal is, we can plug in to the Excel formula, the norm.s.imb, put that decimal in, and it's going to spit back to us the Celsius degree temperature that we need for this particular problem. So if this is less than, we can plug this in directly to the formula. If this is greater than, we have to subtract it from 1 first. And then recall from the one that we did just at the very beginning of the video, if something is between Had it been one of these types of problems where we had the probability, we would have looked them both up and subtracted them in order to get the answer. Um, and that is this one here. But hopefully that will help you through these 4 problems.